Let's take a look at our first example. We would like to show that the absolute of f of x minus L is less than epsilon. Well, the absolute of f of x minus L is less than epsilon if and only if the absolute of x plus 1 minus 2 is less than epsilon, if and only if the absolute of x minus 1 is less than epsilon. Okay. If we let delta equal, let's make it a little bit nicer delta, let delta equal epsilon, then if absolute x minus 1 is less than delta, then the absolute of x minus 1 is less than epsilon, which implies that the absolute of f of x minus L is less than epsilon. Thus, the limit as x approaches 1 of x plus 1 equals 2, okay, by definition. Now, this one might not seem too rigorous. It might seem like, where's the trick, what's going on? Because the function that we used to express delta in terms of epsilon was simply delta equals epsilon. So let's take a look at an example. It's a little bit more complicated. In this next example, there's a small typo. This should be a 2. So the limit as x approaches 2. We would like to show that the absolute of f of x minus L is less than epsilon. Well, the absolute of f of x minus L is less than epsilon if and only if the absolute of 3x plus 1 minus 7 is less than epsilon. If and only if 3x minus 6 is less than epsilon. If and only if 3x minus 2 is less than epsilon. If and only if 3 times the absolute of x minus 2 is less than epsilon. If and only if the absolute of x minus 2 is less than epsilon over 3. Let delta equal epsilon over 3. Then, if the absolute of x minus 1 is less than delta, then the absolute of x minus, or x minus 2, I should say, 2 is less than delta, then the absolute of x minus 2 is less than epsilon over 3, which implies the absolute of f of x minus L is less than epsilon, using our if and only if statements. Thus, the limit as x approaches 2 of 3x plus 1 equals 7. What you can notice about this is that the main work here is creating this link of if and only if statements. That we get a bound of our f of x minus L is less than epsilon with this bound for our x minus our a, using if and only ifs the whole way, which is really, really nice. Now we're proving something a little bit more abstract. We're going to assume that the limit exists and prove that if we have c times f of x, that equals c times our limit. Okay. Now, if c equals 0, this is straightforward. If c equals 0, it's straightforward, so we'll ignore this for now. Given the limit as x approaches a, f of x equals L, we know that there exists an epsilon prime, or we know that for epsilon prime, there exists a delta prime such that if 0 is less than the absolute of x minus a, which is less than delta prime, then the absolute of f of x minus L is less than epsilon prime. So no matter what epsilon prime is, there exists a delta prime such that this is true. Okay. Using this, we would like to show that for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute of x minus a, which is less than delta, then c, the absolute of c f of x minus c L is less than epsilon. We start by picking epsilon. Okay, so we want for all epsilon, we start by picking epsilon. Once epsilon has been picked, let epsilon prime equal epsilon over the absolute value of c. This is really nice. Why is it really nice? Well, if we have the absolute of c f of x minus c of L is less than epsilon. Well, this is true if and only if c f of x minus L is less than epsilon, which is true if and only if the absolute value of c times the absolute value of f of x minus L is less than epsilon, which is true if and only if the absolute value of f of x minus L is less than epsilon over c. Or the of f of x minus L is less than the absolute of f of epsilon over the absolute value of c, which equals epsilon prime. Okay. Well, by or as the limit exists, as the limit as x approaches a of f of x equals L, we know that there exists a delta greater than 0, such that if 0 is less than or equal to the absolute of x minus a, which is less than delta, then the absolute of f of x minus L is less than epsilon prime. Which means the absolute of c f of x minus c L is less than epsilon. Thus, our limit is proven. The limit as x approaches a of c f of x equals c.